We're good.
Okay.
Go on.
So, my name is Armin Nikashirazi. I study at the University of Michigan, Ann Arbor, and I'm going to be talking about an original idea that I believe helps make sense out of the Copenhagen interpretation of quantum mechanics. As you know, Copenhagen is the most widely accepted interpretation of quantum mechanics, but it doesn't seem clear what it's really telling us about the mathematical formalism. And I'm going to present now an interpretation that is very new, and unfortunately, an unavoidable feature of very new ideas is that they're going to be unfamiliar, and they might seem strange, but I hope that you will still consider them. And it attempts to answer some of the why questions you could ask for the Copenhagen interpretation. Why does a component system not have definite properties before it's being measured? Why is there a cut between the quantum system and the classical observer? Why is there wave-particle duality? And I'm going to give the answers suggested by this framework towards the end of my talk. It really requires a completely new way of looking at this. All right, so because this is very new, I want to give a couple of plausibility arguments, some motivational observations. These are strictly mathematical observations. First is, if you consider the two objects that have the same shape but different size, the smaller object has more units of area per volume than the larger object. A reasonable way to interpret this is to say that the smaller object is not only smaller, but it is also more two-dimensional. At the scale at which quantum behavior becomes predominant, so if you take, for example, the Bohr radius as a representative scale, this difference becomes enormous. For the Bohr radius, let's say 10 to the 11. So that's just, the Bohr radius is just an example to illustrate this. The second mathematical observation, as far as I know, has not really been recognized yet. So it might seem unfamiliar, but it is a very simple, actually, and after the fact, hopefully you're going to say, oh, but I didn't think, I think of this. And that is that if you try to represent an object in a higher dimensional space, those properties that depend on the higher dimensional space coordinates that are not contained in the within the object itself have to be represented in such a way that you have to take into account all possible ways it could be represented. So what I just said probably didn't make a lot of sense to you. It's actually very simple and easily illustrated by an example. Take a point x naught, y naught, some arbitrary point, in Euclidean 2 space, and try to represent it in Euclidean 3 space. How would you represent it? Anyone? All right.
On the zero plane.
No, that's a common mistake that people make. That point is a point x, y, 0. It contains additional information, the third coordinate. This doesn't have it. The way to represent it is as an infinite line, infinitely long line. Or to put it more provocatively, as a superposition of an infinite number of points that have common x, y values, but differ in their z coordinates. Furthermore, if I do attribute a third coordinate to this point, this infinite line collapses to just that point that has those three coordinates in that space. So that leads me to assume that there are two ways to construct an infinite line. Either I can construct it by only specifying two coordinates and not specifying anything else, or I can specify it by specifying an infinite number of points. And the comment, it appears to me that right now, the predominant way of looking at it is there's no difference between them. But there is, and it's very easy to show that there is. And to give a label to these differences, this is our usual way of thinking of it. I'm going to call this an actual line. It's an object that actually exists in that space. And I'm going to call this an actualizable line. This is an object that, it looks like an object that actually exists, but it's not. It actually exists in the plane, in the two space. So what are some of the differences in the properties? Well, the metric intervals that apply, the metrics that apply to them are different. One is for 2 space, the other one is for 3 space. The actual line is locally displaceable. What does that mean? I can define a finite segment, a segment of finite length, and change the xy just for that segment, and that displaces that segment. For the actualizable, I can't do that. If I change xy, I change the entire line. So there's a difference. They're not the same. The amount of information that is contained in the actualizable line is just 2 coordinates. The information that is contained in the actual line is an infinite amount of information. The effect of adding information to the actualizable line, as I already showed, is to collapse it to a point. The effect of adding information to the actual line is nothing, because you're just duplicating information that it already contains. So there are some mathematical differences, and again, as far as I can tell, I've looked and I've had discussions with, it doesn't appear that this has been recognized, and it's such a simple thing, actually. So there are clear mathematical differences between these two, and that suggests that really there are 2 modes of existence. Our current worldview is either something exists or it doesn't exist. And what this suggests is that this is incomplete. Either something exists or it doesn't exist, or it could actualizably exist. And this is the part that nobody, as far as I can tell, has really recognized. So the actual is just what we intuitively think of existing. The actualizable is the thing that exists in a superposition. It always exists in a superposition. Why? Because it's missing information. So as a result, the way to represent it is all possible ways that you can represent it. So it's always in a superposition. And it collapses when you put in the information. Okay? So again, evidently this is not recognized. So I tried to apply these ideas now to a framework in space-time. So everything that I just said, I'm going to now attempt to apply to space-time instead of Euclidean space. So I assume, remember, smaller, at smaller scale, space is not just smaller, it's more two-dimensional. I assume that there's a limit where it goes basically, the ratio of the area to volume goes to infinity. Volume vanishes, in other words, and all you're left with is two spatial dimensions. And space-time in that limit reduces from a 3 plus 1 to a 2 plus 1, which I'm going to call Areatime, because 2 plus 1 space-time, to me, to my ears, sounds like a contradiction. So the question then becomes, how could you represent an object in this limit, an object that exists in Areatime, in space-time? For the space-time object, we know that the metric interval is associated, it's proportional to its proper time. The proper time is what you need for the worldline. The worldline is just the integral of the proper time. So this is straightforward. But how do you represent something that doesn't have it? Because clearly these are not the same. This is missing a part. The metric intervals are not the same. That means the proper times cannot be the same. They have to be distinct. So how do you represent it? And I assume that the way to represent it, just in exact analogy to the Euclidean example I gave to you, that you have to represent it in terms of a superposition of all possible worldlines, which, however, are not like worldlines of actual objects, because again, they exist because there's something missing, and it's filling it in by taking in, representing it in all possible ways, and it can collapse once that missing information is filled in. There's another question that comes into that you have to ask is, how do we compare the passage of time along the word lines, the actualizable word line, because you have two metric intervals, two proper times that are distinct. So I postulate that there's a symmetry. So this is all packaged in this one mechanism, basically. So the first step is you have to represent the two proper times in an abstract plane as being perpendicular or orthogonal to each other. Why orthogonal? If they were not perpendicular, if this was a little bit, more, you could project one proper time onto the other. what does it mean to project the proper one time onto another? Operationally, it means if you have two clocks ticking, one according to this, one according to this, if you can project it, then while the one clock is ticking, the other one is ticking too. It's ticking maybe more slowly, and it gets closer, as it's projected more, but it's still ticking. Whereas if it's perpendicular, while one clock is ticking, the other one is not ticking, and vice versa. So in that sense, you can imagine that. So the reason why that's important is because we know from special relativity, you can have clocks ticking at different rates without saying that they tick according to distinct time dimensions. So they cannot be ticking at the same time, basically. So the way to compare it is basically indirectly. You define, and again, this is a postulated mechanism. You define an amplitude to go around at some period. You define and the period is going to be proportional to the proper time of the, an Areatime. So I'm going to symbolize it by tau sub A. If tau sub A is proportional to this period, and certainly tau is in the same plane and it's subject to the same environment, if you will, then tau is also proportional to that period. So that way you have a way of comparing them indirectly. So one of the things that comes out, because one is a proper time and a smaller limit of the other, is that there are going to be endpoints, and basically the proper time in spacetime can just go on, but for the other one, it's just the proper time associated with a limit, which is a very small period. So what happens if the period is longer than the, if you're considering time intervals that are longer than tau sub A? So that's here. So it's assumed that the endpoints are identified, which means it becomes periodic, but also it implies that the same Areatime proper time interval is compared to subsequent space-time proper time intervals. But what that means is that this rotation of the amplitude is not in the same plane. It turns this into a Riemann surface. So because after each period, you no longer end up in the same plane. But if this is a Riemann surface, that means that tau sub A has to be modeled as an imaginary quantity. So out of this setup, this geometric setup, comes this idea then that this proper time has to be modeled as an imaginary period. The relevance is, of course, the quantum mechanics. Why does the fundamental equation in quantum mechanics have the square root of -1? This suggests a possible mechanism, because one of the solutions of the time evolution is a phase factor, which I'm going to get to in a moment. So I'm going to skip that part. So I'm going to now. So this is the overview. I'm going to get to the mathematics in a moment because these are unfamiliar ideas. So I wanted to give kind of a conceptual picture. So the way I would do it is, I take each word line, consider a path. The path is not an actual path like the path of this in space-time. It's a path that is a representation of something that exists in Areatime. And associated with the path, the normalized phase factors that I'm going to derive from this in a moment. Why do you associate it? Because it's not an actual path in space-time. It's a path of something that exists in Areatime. The proper time associated with it in Areatime has to be matched against the path as it appears in space-time. And so this is a mechanism for comparing it. That's why you have to associate it. You integrate over all possible paths. You substitute the appropriate expression for tau sub A, and then you get the final path interval. The only difference is that in Feynman's original formulation, these paths are just real paths, like classical paths, whereas here, I'm making a distinction. They're actualizable paths. They're not actual paths. Okay, so these are the axioms. The first axiom defines the limit. The second axiom basically, assumes this, that leads to this, gives the assumption that leads to the superposition. The third assumption postulates this mechanism for comparing the passage of time. And the fourth axiom is I'm going to talk about that, what happens when you exceed the limit. So when you exceed the limit, that's where space-time comes in, and then that's going to be what is going to correspond in our current parlance to the measurement. Okay, so now I'm going to go into the little bit. Well, I don't know if I have time to go into the mathematics, but okay. So this is the angle in this abstract plane is given by phi, and I can just do a simple transformation where these become units by defining theta equal to cotangent of phi, and then every point in the space is given by cosine this plus I sine this. Of course, you know that's okay. This is each is a I z factor. The reason why there is a factor of I here is because tau A is imaginary, so I have to divide by I to make it real. So therefore, also e to the I to that factor is going to cancel out. So this is actually imaginary, even though it doesn't have an I explicitly in it. And then I do this for a single free particle. The appropriate substitution is this term. I substitute that. I end up with the relativistic action for a single free particle. I can take the non-relativistic limit, define a term for the rest mass, then I associate this phase with all the possible paths. This part is actually pretty well understood. This is just the straight path, path integral of a single free particle. You chop up the path into little segments and sum, and you use a Gaussian integral form and so forth. You define the propagator, and this part is all understood, actually, the mathematics. So if you need me to explain that, I'll be happy to do that, but this is really not the new part. At the end, you end up with something that looks like the final path integral derived from the initial wave function, giving you, the wave function. But because the paths, the worldlines, were actualizable, the wave function that you derive from this also has to be actualizable. There is a long-standing debate about the wave function ontology. Does it really exist or does it not exist? Sometimes you don't know if a question is meaningless and or doesn't, is wrong, or and here I believe it is, because the question assumes something can either exist or not exist. End of story. And what we have here is that actually the wave function actualizably exists. Then the fourth axiom, basically, I didn't have time to talk about it too much, but the idea is that, well, what is an object that is associated with a property? It's something that has mass. Mass is associated with a finite proper type. So mass has to also be considered, as part of this distinction. So the idea is that when this limit is exceeded, mass actualizes, so it becomes actual. It attains, an actual. It is associated with a space-time proper time. Then that means the worldline associated with it is a space-time worldline. The superposition of all the actualizable worldlines collapses to just one actual worldline, and you end up from a superposition of a system to just one actual system. So that's the idea, basically. All right. So let me now give the answers to the Copenhagen why questions. Why does a quantum system not have definite properties prior to measurement? Because it does not actually exist in space-time. It only actualizably exists in space-time. It actually exists in Areatime. Why does a quantum system obey the principle of complementarity, wave particle duality? Because in some experiments, when you're measuring it, you're basically you're doing something that causes you to exceed the limit, and what you're measuring is an actual space-time object. In other experiments, you're just looking at the manifestation of something that exists in Areatime, and because when it's in Areatime, you have to have this mechanism that compares the proper time, dimensions, which gives it wave properties. You get the wave-like manifestation. Why is there a cut between the classical observer and the quantum system? Because the classical observer exists actually in space-time, whereas the quantum system only actualizably exists before it emerges. And the last part, I wanted to talk about entanglement. That this is, I think, really compelling because it gives such simple explanations for this, very seemingly mysterious phenomenon. So basically, the explanation given by this framework is that because the phase factors are ultimately derived from this term, and this term is, comes from comparing the proper times that means that when the wave function describes multiple objects and is not separable, then all of those objects are associated with the same Areatime proper time. And that means that in Areatime, they're in the same region. They're local in Areatime. So this is maybe a little bit too easy of an explanation. Let me give you an intuitive illustration in Euclidean space. Consider this object which can be decomposed into a square and a circle, and suppose that I want to represent it in space-time. How would I represent in Euclidean 3 space? How would I represent it? Well, this is not how I would represent it. What it would be, and it's hard to draw it, is an infinitely long cylinder consisting of a square part and a circle part. Now let me contrive a situation where at 2 times t1 and t2, I could add a third coordinate and thereby collapse one of these two parts. But I didn't know ahead of time which one. So let's say I collapse the circle part at t1. I would immediately know that at t2, I'm going to get a square part, even though it would be wrong to say that at t1 there's a square part. At t1 there's nothing. There's only an actualizable manifestation of the square. But at t2, you get when you then supply the second part, then you get and what you get is basically a system of correlations that's exactly like in quantum mechanics, and it explains it. So in such a simple way, in my opinion. So how about the EPR and special relativity? A lot of times people say, oh, the next speaker after me is not showing up, right? So
yeah,
I have to be a little bit.
Time.
Okay, but I'm almost done anyway.
Yeah, okay.
So there's a tension a lot of times. A lot of people think between special relativity and EPR. So how does this express it? So one way you can represent it. This is the original EPR, which was a correlation between the relative positions. So A and double A are correlated, and B and double B are correlated. If you measure A, here, the other person is going to measure the other entangled particle at AA, and so forth. So in this frame of reference, all 4 measurements, and I'm assuming that they're going to measure this, are simultaneous. But let's assume that I actually measure, the particle at A here and double A, and the measurements here reveal no particle. Okay. So in another frame, in another inertial frame, and what these are samples of the path. I can't draw all possible paths, so I just drew 2 for each, to stand in, and they'll get the point across that I want to make. When you consider the EPR from a path integral perspective, what you get is, suddenly, by switching the frame of reference, you have introduced new space-time events. If you consider these as actual worldlines. If these are actual worldlines, they terminate here if the influence goes at infinite speed. If it goes at slower speed, then it's some other slope. But I'll assume, the best case scenario for this. And that means that the occurrence of the space-time events, which is a termination of the worldlines that contribute to the path integral where you're not going to measure something, depend on the frame of reference. Now, we know from special relativity that sometimes the order of the events can be frame dependent, but not whether they actually occur or not. So, can I just make a testable point?
One more.
All right. So this is more than a prediction because more than a interpretation because it makes a prediction. The argument is very simple. Photons are pure quantum mechanical because they're measures that cease to exist. So they have to exist in Areatime. There are other arguments which I don't have time to get into. General relativity is our theory of gravity, which describes objects that exist in space-time. And the prediction is that if photons exist in Areatime, they cannot produce. They're not in the domain of general relativity. And this is probably as ridiculous sounding a prediction as if somebody before Michelson Morley had predicted that the speed of light is the same in every frame of reference. Okay, thank you.
Thank you very much. Now we have 5 minutes break.